Hey class, it's Mr. Hofstad here with lesson 3 of unit 5. We're looking at vertical circles today. Last class was on horizontal circles. Those ones are a little bit easier because we don't have to think about gravity. But here, with a vertical circle, we obviously have the force of gravity acting always on an object as it goes in a vertical circle. When we're talking about vertical circles, you can think of something like a Ferris wheel, right? We're going vertically up in the air along this uniform circular path. You can also think about now spinning a yo-yo in an up and down or a vertical circle, right? So when we're looking at vertical circles, right, it's important to make sure we're drawing our full force analysis diagram, our free body diagram, with all of the forces acting on it, and especially not forgetting about our force of gravity, because that's going to play a big part in our net force equation using Newton's second law. So in a vertical circle, right, if we're thinking about this in terms of tension, right, so that would be a yo-yo attached by a string to the center of our circle, right, yo-yo on a string spinning around in a vertical circle, going around and around with a constant velocity, right? So velocity, again, tangent to our circular motion, and it'll continue along there. We're going to have maximum and minimum tension at different points. Obviously, that tension in the rope will be at a maximum when it's at the bottom. Okay, so let's kind of break that up. So when we're considering an object swung in vertical circles using a string, we want to assume that the object is moving at this constant speed, so it actually works with all of our uniform circular motion formulas, so it needs to be at a constant speed. So if we're just looking at this bottom part here, we have a net force that needs to be in the same direction as acceleration. So if you remember from our previous lessons, centripetal acceleration always points towards the center of the circle. So when we're at the bottom, that means our centripetal acceleration needs to point up towards the middle. Also, remember our centripetal force is whatever is changing the direction of our object and allowing that centripetal acceleration to occur. So in this case, it's the tension in the rope that's going to be changing the direction of our object or our yo-yo that's being spun, right? That's this tension force in our string is providing this centripetal acceleration, right? It's causing that centripetal acceleration. So if we look at the Newton's second law here, right, our net force is going to have a positive tension force because it's up. It's negative force of gravity because it's opposite, it's down. So our force of tension minus our force of gravity is equal to the mass of this object times our centripetal acceleration, AC. So if we combine that all, the net force at the bottom of the swing is equal to Ft minus Fg, and that's going to be our maximum tension, since the tension force is, if we're solving for Ft in that equation, we're going to add the mass times the centripetal acceleration plus the force of gravity, Fg. Right, so this becomes our tension force equation. Okay, so if we think about that logically, when you're swinging a yo-yo, it's going to be most likely to break at the bottom. Right, that's going to be when it feels the heaviest. It has to fight against gravity the most there. So gravity is fully adding up to this tension. Now let's look at the opposite scenario. When we're at the top of our swing, we still have the same mass, so therefore we have the same force of gravity. But when we add everything up together, our net force is going to be, well, since they could be negative Fg, negative Ft equals negative MAC, but just for simplification, right, multiply that all by -1, and we have force of gravity, which is in the same direction as tension force, so we'll add them together, is equal to mass times centripetal acceleration, also in the same direction. So now when we solve for Ft in that equation, right, here's our equation. If we want to solve for tension force, we're going to subtract force of gravity from our net force, mass times centripetal acceleration. So yeah, we are using down as positive for this, right? If you did use negative, right, all of those would be negative. That will give you the same answer. It's just a little bit cleaner, a little more structured to just flip them all to positive because we like working with positive numbers. So here the tension force is our net force, right? Mass times centripetal acceleration minus force of gravity. So that's going to be the smallest amount. And if you did any in between, right, you're going to have maybe minus half of Fg or some fraction of those together. Okay, let's try an example out. So we're looking at a 28 kilogram object. So we'll draw it out. It's at we want to find minimum tension, right? So with minimum tension, we just went over this. We know we're going to have this at the top of the swing, at the top of our vertical circle. Right, if it were to say maximum, we would put it at the bottom. Here it says minimum, so we'll draw it like this. There's our object attached to a string to the center. We have to add all our forces. We have force of gravity acting down. We have our tension force acting down. And we have this centripetal acceleration and some mass of our object, which is all given to us, or everything that we need. So using circular motion, which is one of our principles of physics, so circular motion, also known as principle of physics 2, we are able, right, to look at this in centripetal acceleration, right, assuming velocity is constant. So our net force equation from this guy, just like we did in our notes a second ago, we're going to use down as positive, right? You could write that, a reference system, down is positive. All right, this is one of the few times we'll do that, and we just do that because it makes everything positive rather than negative. So this will be F net is equal to Ft plus Fg, all right, and that'll be equal to the mass times the centripetal acceleration. So this question wants us to determine the length L. So this is what the question wants from us, that length. That length is also known as the radius of our uniform circular motion, and that's what we're looking for. So we're going to need to use one of our formulas for centripetal acceleration with the radius in it, which is both of them. So we're going to look into the question more. We'll just write down everything they tell us. So the mass is 2.8 kilograms. That doesn't affect our centripetal acceleration, but it will affect our force of gravity and our centripetal or net force with centripetal acceleration. Now we also have our period, which is 0.72 seconds. So every time it goes around, takes 0.72 seconds. And we know that this Ft in this scenario, when it's at minimum, is equal to 20 newtons. Oh, sorry. Now we're looking to see which of our centripetal acceleration formulas we can use. So since we have period, we're going to be using our 4 pi squared r over period squared. They don't tell us anything about speed. We don't really have a way of determining speed. They do tell us period, so we'll go ahead and use that. So solving this with our radius as the unknown. Actually, first we're going to need to solve for AC here, because this is our unknown. We need to actually come up with a number for that using this equation here. So if we rearrange this, our centripetal acceleration will be equal to, if we divide both sides by mass, it's going to be force of tension plus force of gravity over mass. So force of gravity we could rewrite as being mass times gravity. All right, those will cancel out. Let's see what number we get. We have 20 newtons plus 2.8 kilograms times 9.81 divided by 2.8 kilograms, giving us a centripetal acceleration of 16.95 meters per second squared. Right, and that's an acceleration that in this case is positive, using our reference system is down. So since it didn't come out as a negative number, we know it's right going down, positive. All right, now we're able to throw this number into our centripetal acceleration formula here. So we'll solve for radius first. Our radius out of this equation, we're going to multiply both sides by period squared. So we get AC period squared. And we're going to divide by 4 pi squared. Just doing some simple algebra here, isolating for our unknown radius, which is actually in this question the length of our string. So we know this, we know that, that's a constant. We're able to solve now. Centripetal acceleration of 16.95 times period of 0.72 seconds squared. Be careful when you're doing questions. Period needs to be in seconds. If it's given in minutes, hours, or anything else, convert it to seconds. That's our standard unit for time. And we're going to divide this all by our 4 pi squared, giving us a radius or a length of 0.22 meters, also known as 22 centimeters. Either of those answers will be correct. Okay, that's our first example. We still got some more to go. Okay, now bringing in an old Unit 3 idea of apparent weight. Physics is all built on our previous knowledge, right? Here's our throwback to Unit 3 with apparent weight. So if we remember, whenever we hear the word apparent weight, we're going to be thinking Fn, normal force. So those are pretty much synonyms, right? If a question is asking you for apparent weight, what it really is asking you for is the normal force or the surface force between two objects, right? The force of one surface pressing against another. So in terms of apparent weight, the normal force will be how heavy you feel, right? Just think about our elevator questions as well. When we're accelerating up in an elevator, we're going to feel really heavy. When we're accelerating down, we're going to feel really light. Here, things get a little bit different working with our uniform circular motions. Don't think of these as our elevators. This is a totally new concept. So apparent weight is our normal force measured by the scale reading. So if you imagine you put a scale right under there, it's going to be the reading on that scale or the normal force for each of these different objects. All right, I like to think about these as cars going on down a big hill or up a big hill. And just thinking about it like that, right, we can kind of come up with an estimation or approximation, a hypothesis of what we think we would feel like as we're going down a hill. Right when we reach the bottom, we're kind of going to be putting some extra weight on the shocks of those car, we're going to feel like we're squishing down into the seat as we're starting to come up a bit. So that's actually where we're going to feel heaviest. We'll prove this mathematically, right, with our net force being the normal force minus the force of gravity is equal to our mass times centripetal acceleration. So just like we did before with our circles with a string, our vertical circles with a string, now we're doing vertical circles without a string using normal force, like a car tire pressing against the bottom of a hill. So if we are looking for the apparent weight, let's remember that's our normal force Fn. If we're trying to solve that from this net force equation, we're going to have our mass times centripetal acceleration plus Fg, right? So out of that comes normal force, apparent weight, is equal to our mass times centripetal acceleration plus Fg. So since we're adding Fg to solve normal force, we're going to feel heavier, right? It's going to be a bigger number. So that's when you feel heaviest, at the bottom of the hill, right? So I guess that's very similar to what we just looked at. Here, we're going to feel heaviest or have the most tension at the bottom, just like we feel heaviest, have the most normal force, right? Where the normal force here is our centripetal force and the tension force is our centripetal force in a vertical string swing. Okay, so now we're at the top, just like before, but now our normal force is pointed up, whereas before we had tension and gravity in the same direction. So again, we'll keep down as positive just because it's apparent, right? And if it's not apparent right off the bat, you'll see quite quickly that this force of gravity is going to be much bigger than the normal force. So we'll have a big force of gravity pulling us down and a small normal force between us and the hill, or between this object and the surface that it's rolling along. So using our diagram here, we can find our net force, which is equal to mass times centripetal acceleration, is equal to the force of gravity minus normal force, because we're treating down as positive. You don't always have to do this, by the way, right? If you do, use up as positive, just like we do for our max tension or our max apparent weight. If we did it positive here, we would just get a negative answer, right? Because force of gravity is bigger, right? If we have a bigger negative than positive, we'll end up with a negative final answer. And that just means that, right, we're going down. So again, these sign conventions or our reference system are super important, but you got to choose. As long as you stick to it throughout the question, right, it'll work. You'll get the right answer. If your answer is negative, if you're saying up is positive and your answer is negative, that means the answer is really down. So if we solve for normal force here, it would be mass times centripetal acceleration minus Fg. So since we're subtracting Fg, right, so if you solve for normal force here, we'll have to add it to both sides, right? Actually, in this case, it would be Fg minus MAC, right? That might be worth writing down. Normal force is equal to Fg minus MAC, mass times, so that's the subtract, minus centripetal acceleration. Okay, and that's when we're going to feel the lightest, because we're subtracting those from each other rather than adding. Okay, let's do our last example. Here we have somebody driving inside a car. They're driving to the bottom of a dip. So if we drew that in, right, we have a car at the bottom here. If we drew in all of our forces, we're going to have the normal force or the apparent weight up, we're going to have a force of gravity down, and our centripetal acceleration is always going to be towards the center of our circle. So in this case, it's going to be up, and we'll say our reference system up is positive because we know that is going to be bigger and our centripetal acceleration is pointing up. That's another way you could think about it. Make your reference system positive in whatever direction your centripetal acceleration is. Just a good way to keep your centripetal acceleration positive in the end. So we got a mass of a person of 84 kilograms. We have a car, so a mass of person, mass of car is 1200 kilograms. So we got our person sitting in the car. Driving to the bottom, we know the radius of this, right? Radius is equal to 15 meters. And our constant speed of 91 kilometers per hour. If we divide that by 3.6, we can get our meters per second, which is 25.278 meters per second. So constant speed, we know we can use our uniform circular motion formula, right? Centripetal acceleration. We're looking for the maximum scale reading. So this person is sitting on a scale. We're actually only analyzing this person and the scale they're sitting on. So if I were to redraw the free body diagram for that, right, just with the circle, we have our person. They're sitting on a scale, right? They're going to have their force of gravity acting down on the scale and the normal force acting up, and they're going to be accelerating with centripetal acceleration upwards. All right, and remember the centripetal acceleration just means they're changing their direction. They're not actually moving or speeding up or slowing down. Okay, so we need to determine the maximum scale reading, which is this guy. So let's write out our net force equation for this. The net force for this guy is equal to our normal force minus force of gravity, and that's going to be equal to the mass of the person, not of the car. We can kind of ignore that actually, times centripetal acceleration. That's kind of a distractor, the 1200 kilogram car. So we're trying to solve for our scale reading. Fn is equal to the mass of the person times centripetal acceleration plus force of gravity. We need to determine this centripetal acceleration. So we've got two formulas to choose from. We don't know period, we know radius, so we'll use we know speed, speed squared divided by radius. So speed in meters per second, 25.278 squared over a radius of 15 meters gives us a centripetal acceleration of 42.6 meters per second squared. Right, and that's going to be accelerating up, right? That's this guy here. So let's solve. We'll throw this in as our centripetal acceleration into this formula. We know mass is 84. Centripetal acceleration is 42.6. And we're going to add force of gravity, which is 84 times 9.81. Right, the mass of the person times gravitational constant. And we get 4,402 newtons. We need three significant digits, so we've got 4.40 times 10 to the 3 newtons. Or you could write it in kilonewtons. All right, that's it. I hope this lesson treats you well. It's a little bit tricky, right, especially working with our coordinate systems. Just remember that whether you choose up to be positive or down to be positive, just carry it through in all your work, right? Write down your reference system. The number one mistake you're going to be making is with those signs here. So Don't forget gravity, don't forget your reference system, and this should work out for you.